So next up, we're going to have a talk from Nikita, who is a data visualization engineer and designer with a background in atmospheric physics and creative technologies. He is the founder of Interacta, an award-winning team of scientists, designers, and engineers who create beautiful and functional tools for working with data. He co-created Cosmograph, the fastest browser-based tool for visualizing network graphs and machine learning embeddings, and he is the author of Univiz, a handy data viz library for the web that integrates seamlessly with all popular UI frameworks. And with that, the floor is yours.
Hey everyone, and in this lightning talk, I will discuss how we can visualize text in the age of large language models and artificial intelligence. And I'm Nikita, and for the past 10 years, I have been creating tools for working with data. Amanda mentioned Cosmograph and Univiz. So a lot of images in this talk were created with Cosmograph. And if you ever work with network graph data or with machine learning embeddings, feel free to check it out. Let's first try to answer the question, why do we even want to visualize textual data? And the answer is simple. In the recent years, large language models have become an integral part of our lives. And the usage of these tools will only continue to grow. And I think that we need better, scalable ways to work with textual data, to analyze textual data that these Gen AI models produce, and data we use to train these models, and security of these models is another big problem because people using your models can use different prompt engineering techniques to hack into a model and abuse your model. And with this recent advantages with LLMs and the growing usage, I think the problem becomes critical. But let's delve into the past a little bit and remember what was the most usual way of visualizing text data, and I think to me it was word clouds. So it was probably the most simple way to visualize text data for a long period of time, and it appeared in the 1990s and was popularized in the 2000s by Jonathan Feinberg, who created a Java tool called Wordle, which you could use to create your own word clouds. And while it looks fun and interesting, it gives you very limited analytical depth of your data set. Well, so technically, what word cloud shows you is just the frequency of terms appearing in your text. And when you're thinking about visualizing text data, you need to measure it first. Somehow, you need to turn text into numbers. And it all starts with quantitative linguistics in 1930s, and specifically with Ziff's law, discovered by American linguist George Kingsley Ziff in 1935. And the law states that the most common word occurs approximately twice as often as the next most common word, 3 times more often as the third most common word, and so on. Later, we had techniques like TF-IDF, vector spaces, anagrams. They became foundational for search engines and recommendation systems. And then a lot of other interesting things happened in the field. And finally, in the last 10 years, we have the advent of transformer models, such as BERT or GPT. And these models allow us to transform your text into a huge array of numbers, sometimes thousands of numbers. We call this an embedding. So it's a huge vector that captures the semantic meaning of your text. And since this vector has thousands of numbers, we call this a multi-dimensional space. So and this is a unique vector space that captures semantic meaning and keeps the semantic distances between different terms. For example, if you have terms man and woman and king and queen, the distances between these two terms in this vector space will be about the same. So let's say you have managed to turn your huge text into these thousands of numbers, but how can you go from numbers to a map? Luckily, we have algorithms for that as well. So we have algorithms like PCA, TSNE, UMAP, there are much more than that, that do what we call dimensionality reduction. So you go from thousands of numbers, thousands of dimensions, onto just 2 or 3 dimensions. So you can draw a map. So let's say you have a point, and every point represents a paragraph, or a blog, or any other piece of text. And then these algorithms, when you run these algorithms on your vectors, they cluster similar texts together. So you can see similar topics in the same areas on your map. And in fact, it doesn't need to be text. It can be any data. It can be sound represented as numbers. It can be image, anything. So on a large scale, when you do this magic, when you apply your algorithms, then you end up having beautiful semantic large-scale maps of your texts that you can go and analyze. And let's look at this example. Here you have more than 300,000 most cited scientific articles. Color here represents a major scientific field. And you can see on this huge map, you have multiple clusters. And interestingly, points between those clusters, they actually interdisciplinary research articles that are in between different scientific fields. And you can easily spot outliers. So if you're working with a huge text data set and you don't know much about it, you can use these tools to go and explore the texts and find anomalies and do something with them if you need to do something with them. And interestingly, since it was a scientific article data set and scientific articles cite other articles, we have another opportunity to visualize this data. You can draw a huge network graph, and where every point is, again, is an article, and there are invisible forces between the articles that cite each other, so they being attracted to each other. So you have another map built using the same data but different technique. And here you still see the clusters, but it lacks the level of detail the other map had. So let's take a look at another interesting example. So here we have about 3 million of chat messages with different large language models. And again, you have probably hundreds of clusters, much more than I had colors when I created this image. But you can see that every little cluster represents a certain topic, and it doesn't tie to language. So this text embeddings, these vector spaces work across all the languages. So you can zoom in and you can explore clusters and search for suspicious things. For example, if we highlight on this map a cluster that has been marked as having malicious prompts, you can see that it ended up somewhere in a specific area of this map. So you can go deeper and you can explore and maybe find false positives, false negatives, retrain your model that flags the messages, or just remove these messages from your data set. And with this, I would like to end my talk and inspire you, encourage you to explore different new ways to work with textual data, because I feel like it's becoming more important to create with new techniques, new tools, because we're going to have unprecedented amount of text generated in the next decade. So we need to find different ways how to deal with this. Thanks.